Okay, folks, as we continue on with our program, we have Dr. Gobeille, Dr. Douglas Gobeille from Providence University.
URI.
URI. I can't keep them straight. Oh my gosh.
Very important.
All righty. We'll take that as a compliment. And he's going to address the topic of death in space today, right? And we have a list of fascinating space objects that he's going to walk us through, and that part of your program kind of caught my attention. So please help us extend a warm skyscraper welcome to Dr. Gobeille.
Yeah.
Yes.
Perfection. Well, thank you all for having me. Yeah, we're going to cover some ground today. This talk is always motivated by the same questions I'm getting everywhere from everyone, which generally comes down to what's going to kill us from space, are there aliens, what's up with black holes. So we're going to kind of dance around a few of those things today. As we're looking at this animation, it's a little laggy, but is indeed there. We're seeing kind of what we would say your local environment. Every one of these little dots is going to be a tracked object that we know about in the inner-ish solar system. Of course, we've got Mercury, Venus, Earth, and Mars here with some of the outer planets' orbits seen beyond that. And of course, this is somewhat germane of a topic because, let's see if we'll advance, there we go. If we look at the cosmic calendar, where Carl Sagan tried to very nicely wrap everything up for us in one calendar year, as I like to joke, it was only a day ago on the cosmic calendar on December 30th that the joke goes, dinosaurs wish they had a space program. In the 65 million years since then, we have continued to be hit repeatedly, which is the normal case of things. What's interesting here, as I like to discuss with my students, is this was a very significant impact. So significant that there is a non-zero chance that there are little teeny tiny little pieces of dinosaur on Moon or Mars, which is a fun place to discuss the idea of panspermia, where it could be this is how life is going to spread throughout some star system or solar system. There are a lot of ways for creatures and life to live once they go into space. We've certainly seen this both in vivo and in vitro. And so while not the focus of our talk, just something nice to think about. It was a significant detonation, if you want to think of it that way. We can kind of try to understand this by using some silly units here. I'm going to put everything in kilotons so we can measure it off of Little Boy down there, August 6th, 1945. Something people tend to think of as a fairly large explosion. It is a small thing. We compare this to the Tsar Bomba, 50 megatons. Here shown as 50,000 kilotons, the largest single nuclear weapon ever made by the Soviets back in the 60s. Off the top of my head, you've got Krakatoa and Tambora. Tambora is the largest recorded explosion in human history, and Krakatoa is just a few decades later. This is like 1815 and 1838, and they are going to be much more significant than our friend Tsar Bomba. If we took all of the nuclear weapons we have today, roughly speaking, we don't know precisely how many there are, but we've got a good feel of it. We're still outdoing Tambora, but we've done nothing in comparison to that very large rock that ended the dinosaurs 65 million years ago, as best as we're concerned, in what we generally refer to as the KT event. Now, this is stuff that is still ongoing today. Space is always trying to reach out and touch you. The question is how big and how often. That's certainly what we can see here. Now, for the most part, what we're seeing on the far left of this plot and kind of up, we make use of a pointer, is the very small stuff that we all love in places like skyscrapers. We would call these meteorites. Things that are small, passing through our atmosphere, vaporizing, give us a lovely show. Wonderful. Things the size of peas to golf balls. If you're bigger than that, you do stand a non-zero chance of making it to the surface. But no big problem. However, as we start to work our way down into the every century region, we're getting to objects that will absolutely make it to the ground. And we'll be looking at that in a moment. As we get down to the more significant events, we're looking at a timeline from millions to hundreds of millions of years. And basically for events like the KT event, they happen about once every 100 million years. And that was 65 million years ago. The odds are not things that say precisely when something is going to happen, but as time goes on, it is more and more likely that we're going to see another such similar event. Most folks here, as I've seen, were probably alive and kicking back in the 90s when we started looking at Shoemaker-Levy 9, which taught us a brief lesson in planetary physics, where a large object is going to get a little too close to Jupiter. Jupiter is going to be able to grab hold of it, pull it apart into several other smaller objects, which are then going to slam into the surface of Jupiter, leaving significant scarring. This, of course, will lead to Hollywood doing what it tends to do, not making one movie, but two movies. We probably all remember Armageddon, the one that did better. We might forget about Deep Impact, which is the better one that did not do as well in the theater. And for a brief moment, the American populace will say, oh man, this could be semi-problematic. And they're going to forget pretty quickly, even though space continues to leave massive bruising on Jupiter all the time. This is, of course, we said, an ongoing effect. We can go back to the early 20th century in looking at the Tunguska event. Almost assuredly a comet air bursting over Siberia, leveling an enormous swathe of land, allowing people on the other side of the world to read their newspapers at night. Fortuitously, I'm always quick to point out, these things tend not to happen in places where people live. As we have probably known for just about forever, Earth is about 3/4 water on the surface and 1/4 land. Not quite precise, but good enough for government work. And of that 25% that is land, humans cover 5% of that. Now we need to be careful with our math because that tells us humans are crawling and living on about 1.25% of the planet. So 99% is where we don't live, and 1% along coastlines, lakes, rivers, places generally with water, is where we do live. Which means most of the time when things happen, they don't happen where people are. They're not that spread out. Of course, they cover the entire planet, but you have entire regions. Just think about the Pacific for a moment. You have more or less an entire side of the planet you can look at, and there's almost no one there if you do that. Russia, being a very large country, has been visited multiple times. This is Chelyabinsk in 2013. We're starting to see more and more of these because we're all starting to carry cameras and video cameras, which makes it a lot easier for start picking up things that were always there, but if you didn't catch it, you weren't going to really know about that thing ultimately. This was a pretty significant event. It is going to detonate with more energy than the bomb that we dropped on Hiroshima and Nagasaki combined. Some people are going to be hurt, but in general, not so bad. This was a bit of a close call. As we said, this is stuff that is still going on. We, in the 90s, decided it would be a good idea to maybe find these things. If you're above 1 kilometer, that is literally the end of the world, as long as you're talking about civilization and most large-scale life. Beneath that, it's just really, really bad. We declared victory in the early 2000s when we said we know where 90% of the things that will end civilization are. And that doesn't bring me a lot of comfort. Because what about the other 10%, where we have no idea where they are? I take a moment here as someone who is, pardon me, specifically a radio astronomer. I do most of my work in radio, some in X-ray, some in gamma ray with space telescopes. But Arecibo, we lost back in 2020, which was kind of the premier radio telescope on the planet for finding and tracking asteroids. Its loss is very hard for me to explain to you. Besides, it effectively goes from your ability to find these things, and I'm going to legally blind you in the sense of your capacity to track them. This is one place where we really need to start putting forth effort again, because as I just mentioned, the odds are not as spectacular as we would like. And the 90% are just the ones that flat out destroy most of Earth. It gets worse from there in terms of how many of the smaller ones we know where they are and our ability to track them, and they can do tremendous damage on a very large scale, while still in theory allowing for civilization to carry on. As we're probably all aware, humans tend to have a bit of a short span of attention on these things. And like I said, you'll notice this goes from, we didn't do this a lot, to, oh geez, look at Jupiter, and we jumped up. But we still have a lot of work to ultimately do here. Of course, Recently, we decided that we were going to try and do something that the dinosaurs didn't do as a joke 65 million years ago. They wished they had a space program. The DART mission was going to be the first time that humanity kind of strikes back in so many ways. Again, knowing my audience here, you're probably fairly well aware of the situation, where what we're doing is we're taking a very classic human approach to solving problems, hit it with something. All right. If it ain't broke, don't fix it. Okay. And this will work perfectly fine. You can use all kinds of lasers and rail guns, or you just throw a mass at it. And that's exactly what we did. We had a spacecraft, our DART spacecraft. We have an observer spacecraft to see how the thing is going to hit it and what the effect is ultimately going to be. We've got our primary asteroid Didymos, and its little moon Dimorphos. Some people call it just a mini Diddy. And what we're going to see in white here is our initial orbit. And in orange is going to be our subsequent orbit. And we can track that impact here. Again, if you're going to do it, bring pictures. And this is you're seeing those last images, that little red blink at the end. We get just a piece of the image transmitted back to the Luciasat before, splat. And thus your camera is not working that well anymore. But what we're going to really see is more than we expected, because in the actual event, it should in theory animate, but it's not for me, that's fine. Is we kind of almost made a propulsion system. It's one thing to just hit an object and change its trajectory. Here, as we go in, we're actually funneling a huge amount of ejecta out, and it was far more impactful, pun totally intended, than we had thought it originally would be. And these are the initial moves to trying to start to change these things. I would mention Didymos was never ever going to be a problem, and we don't know where a lot of the problems are. The earlier we discover any of these things, the more ultimately that we can really do about it. The idea is the closer your target is, the worse your aim can ultimately be to still hit it. The farther and farther and farther away we go, the precision must be very high. If a rock or a comet comes too close to Earth, you need to move it very forcefully if you're finding it early on. If we know about it decades in advance, we can just give it a little boop, and that will be just about everything we need. We just need to give it a small nudge off of its course. And right now, we've shown we have the ability to give small nudges. We are getting better at this as time goes on. The teens of this century was kind of looked at as the dwarf world time. We were going to so many asteroids and comets and visiting them and starting to play around with new ideas such as this. I would be remiss to say, though, however, rocks are not the biggest thing I worry about ultimately. Rocks are pretty easy to deal with. We already have some mechanisms to deal with them. As long as we know they are coming with some reasonable period of time, in theory, it shouldn't be that big of a deal. Unlike the giant thermonuclear reactor in the sky that keeps everything going, our friend Sun. Generally a good neighbor, but not always. And that's certainly what we're seeing here from the Parker Solar Probe. It is an ongoing and active environment. What we're seeing here is clear evidence of what we generally call space weather or solar wind. Sun is always spewing material out into space. The question ultimately is how much in any given moment. And some of these events with Earth here shown to scale are pretty titanic. Now, historically, again, we can see that again here with a solar flare, we have had some pretty significant problems. Mostly right now, the biggest issues are for convenience. We have had problems historically, like in Canada, Quebec, Montreal. Back in 1989, there were some significant power outages based on Sun producing some of these events here, like solar flares. We have semi-hardened the electrical grid against such things, but we still remain quite dangerous. Some of you have noticed that we have poor reception on some days that can be associated with solar weather. Same with your GPS. And that's because there is this always and constant ebb and flow between Earth's magnetic fields and Sun. On a normal day, we're getting just a little bit of aurora. We kind of go to here, and that's fine, except this is energy that has gotten through two of Earth's primary defenses. Those are your inner and outer Van Allen belts. And it's slamming into your final line of defense, your atmosphere, which generally does a pretty good job of holding this off. The problem is when it doesn't, like is what's happened in the past with very large effects. The big one we tend to talk about is we point back to 1859 and the Carrington event. where we're going to put so much energy hitting Earth at once that we can do things like have telegraph operators between Boston and Portland, and they're trying to talk to each other, and they say, disconnect your battery, would you? And both of them disconnect the power sources for their telegraph, and they say, actually, this is easier and better. Sun is powering the telegraph system for a short period of time. It's going to overload some things, sparks will happen in some places, some fires come out, some people take some pretty decent amounts of juice, no one dies. But for a little bit, global telecommunications is not great, because mostly the telegraph. That's 1859. Today, the effects would be cataclysmic. The estimated value of loss for just the United States ranges from $5 to $10 trillion if an event like this happened. Because effectively, you would wake up, everything would seem fine. This does not kill you or biology or life, but your phone won't turn on, your computer won't turn on, your car won't turn on. Anyone who's hooked up to anything electronic to keep them alive, they have sadly left us. And it's just going to get pretty bad. As I say to people, we've seen a taste of this now with COVID. COVID helped me with a lot of these discussions where small disruptions to the system can be pretty significant. What's even more interesting with looking at events like the Carrington event, I can again kind of joke with the crowd I have here. I love all of my old LPs. I joke with my students about this. They're still doing just fine. I could break it over your head and it will break your head first and the LP second. We're moving now to this, which is great, which is fine, which is wonderful. And we're producing more media, more art, more music, more videos, more words than at any other point in time. But I have to point out that we're existing in this inverted pyramid of information where we still have cave paintings from tens of thousands of years ago. We still have, every time humans have really carved into rocks. My LPs will survive this. Most modern media will not. And where we have put all of our stuff is something a lot more volatile than it was before. The sun-facing side of the planet is what will get walloped. And it's possible that we'll be able to hold on to a lot of this, but when suddenly one side of the planet does not have and the other one does have, that's a world war. That's not going to go very well. This is going to be a bad, bad day for humanity. I'd love to think that one side of the world will say, we'll save you and we'll help you. I'm not convinced at this point in time. So again, this is for me way worse of a problem than rocks because we can't stop it. There's nothing that we can currently do about this. Some place will survive. If we think about NORAD, which we purposely put underneath Cheyenne Mountain, we literally put a mountain on top of a place so it could survive pretty much anything we threw at it. Some military installations like that will be okay. But for the most part, anything electronic is probably going to get fried. And that is going to be a bad day. Even if we set ourselves out to Moon, Moon is right next door to Earth. We're discussing the effects of a shotgun blast in this regard. This is not a precision strike. That wouldn't help us either. The side of Moon facing Sun at that time would have all the same problems on Earth and way more being on Moon. It's more of an idea that we need to start spreading ourselves out with our new capacity. In the same way we can launch larger payloads now and take care of rocks a bit, the answer here is spread your eggs out. We need to be in more places in the solar system. Because the idea of Earth and Mars being in a semi-line definitely happens periodically, about once every 2 years and change, but the rest of the time they're not so much in straight lines. The idea of tagging both would be pretty low. It could absolutely happen. So spread out even more. And as we keep spreading, it makes it easier and easier for one place to get impacted and the rest to potentially survive. Let's go to another problem. So back in the 70s, we said maybe we shouldn't be detonating nuclear weapons on the surface of Earth for so many reasons. So we went underground. And this is what leads us to our SALT 1 and SALT 2 Strategic Arms Limitation Treaty talks. And it's that classic bit of government business of trust but verify. And so the Vela satellites are put up into orbit of Earth because when we detonate a thermonuclear weapon, in general, we can identify this by a telltale flash of gamma rays. And almost immediately, we start seeing these flashes of gamma rays. But none of them are coming from the planet itself because actually people were mostly holding the line. Excellent. We're seeing some of those mapped out across basically a decade here from 2004 to 2015. And what we can see here is we've superimposed upon this the Milky Way and where all these events are. And it immediately tells us that what we're looking at is an event that is not in the galaxy. Certainly some of them could be, but in general, all of these are happening from outside of the galaxy. We've gone from problems of potentially within your solar system to problems that aren't even in your local region. I'm not going to talk much about supernovae today. People can certainly ask me some questions. I'm going to try and leave some room at the end to talk about the other things, because there are no stars anywhere close to Earth that ought to blow up and cause problems anytime soon, that we know of. Those are the big ones. We tend to know where they are, and the small ones have to have a friend, and we tend to know where those are too. But these are random, and worse off, they're single events. They only happen the one time. And these are what we call gamma ray bursters. Now, on one side, we've got long duration bursters. And these will come from the awesomely named hypernovae, or collapsars, where for very large stars, the core will collapse almost immediately into a black hole. See how I'm going to transition from death in space to black holes? And we'll start to try to consume the star from the inside. It's an event like this where I need to say to you, black holes are terrible at eating things. Absolutely horrible. I like to refer to this back to, let's go to Cookie Monster, because I think everything I learned I got from Sesame Street and the Playgrounds. Those are the two places I learned everything I need in life. Cookie Monster tries to slam a bunch of cookies into his mouth and throws them pretty much everywhere. He lacks a trachea, so that's problematic. But with our black hole, it's going to be the spinning of it, and it's going to take anything that's near it and shred it and spill it everywhere, and very, very little will go in. Black holes, unlike the classic 1978 movie of the same name, are terrible at eating things. I really have to stress that to people. They're not infinite in their gravity, they're not infinite in their mass, and they're generally really hard to fall into. We'll talk about that in a minute, but I want to say in this case, it is going to feed because we're literally going to park it inside of a star. So this is a forced feeding event in so many ways. And once it consumes a piece of the star, if we go back for a second and go through this, you'll notice it definitely doesn't eat all of it. That's where this stuff is going in the other directions. It's still going to be a fairly sloppy eater. But in this case, we are forcing some food down the gullet. This is why we literally talk about the mouth and the throat of black holes in terms of how we push things down there. This is how we produce what we call a long duration gamma ray bursters. Those are 2 seconds or longer. There is another way to do this, which is slamming together neutron stars, a different type of dead star. And we can get a short period burster, which will give us the same overall effect. Did I miss a slide? I think I may have. Yep, there it is, but I don't know how I'm going to get it to go. So that will be tricky. Still, when we do this, we have 2 different mechanisms to produce an enormous amount of energy. And it is so enormous because of what we're seeing here. Rather than in a normal supernova, where we'll spread all of the energy, as we would say, isotropically, in every possible direction, going everywhere. Here, this is a beamed event. This is the difference between a light bulb and a laser. And this allows the energy to remain highly collimated, thus allowing huge amounts of energy to be translated across the gigantic distances in space. Events like this could easily sterilize one side of Earth, the side that is facing the event, if you got a head-on strike. These are things that from other galaxies a few times have been visible to the naked eye, if you knew when and where to look. And that is incredible. Most of the stars that we see in the night sky are literally the biggest and the brightest ones. It is an uber selection effect. You're literally seeing only the tallest people out there. You're just thinking they're all huge giants. This takes that to an extreme. It is at least outside of your local group. We are talking about thousands and thousands of times farther away than the nearest galaxies. And still we can easily see them from time to time. The energy is extreme. And these are just 2 ways of a number of ways that we can produce black holes ultimately. So let's transition into that. I would be quick to say there are so many ways to kill life on Earth, and I've only touched a handful of them. I'm happy to discuss more with you in a little bit. But let's talk about this. I love the English language. There's a way to describe killing you in so many different ways. My favorite has to be defenestration, throwing someone out of a window. You're so complete in this that we have a term for death by black hole, spaghettification, where if we did manage to get you really close to a black hole, which is a reminder, no starship in the future is ever really going to have this problem. If you got sucked into a black hole, you earned it. I mean, you must have worked really, really hard in order to make that work. They are incredibly easy to see, as we'll see in a moment. We'll still justify that. But still, you in theory would get sucked in. We're going to slowly stretch you out into a giant line of your own particles, thus spaghettification. If we're just thinking about this, think about the medieval rack where we're going to kind of have you like this and just start stretching and stretching and stretching. We're going to start to pop you at your elbows first and your knees. Then it's going to be your spinal column here, then your wrists, and it just gets worse and worse as time goes on. As I like to say, the energy, time, and effort required to pull off this stunt, you must be the worst person ever. There are just so many better ways to get this done. This would take so much energy. It's very hard to describe. Even an advanced civilization would have to task themselves with doing this. It would be just easier to do it with any other thing you could think of. Still, I said, black holes are going to be tricky for you to ram into because while by their definition they do not of themselves give off light, that is in the definition, as I mentioned, they are very sloppy eaters, as we see in this rendition of Cygnus X1 here, where what we have is a black hole, kind of obviously I think right there, eating its nearby companion star. And this is fairly common in space. Why? Because solar systems like ours with a single star are actually the rarity. They are the minority case as best as we're concerned, probably 20% or less of the stars in the Milky Way at least. Binaries are the most common, and we can stack 3, 4, 5, 6 stars together. And when you do that, they will frequently start to interact with each other. And so if we have a black hole with anything nearby, it tends to make itself well known. This is at the stellar scale. I do not study stellar black holes. I study supermassive and ultramassive black holes. Here, we're looking at a galaxy, and the black hole at the center is doing its business and injecting all of this matter outside of the galaxy, influencing a region larger than the galaxy itself. And this is what I mean when I say it's just really somewhat outlandish to think you would ever ram into a black hole. There are some that are very old and they have spun down and there's not a lot of stuff in their environment, but they are very small. And so again, you have to have high precision aim around that. And again, there'll be other evidence you'd probably be easily able to see of the fact that something big happened here in the past. There might be a black hole nearby, as we'd say here in New England. All right, well, we've kind of covered the big things with black holes. I do want to repeat them because it is definitely where I do my work and where my passion is. They do not have infinite gravity. They have the same gravity of anything else of the same size. While supermassive black holes are some of the largest single items in the universe. Sagittarius star at the center of the Milky Way is 4 million suns worth of material. The galaxy is over 1 trillion to 10 trillion solar masses worth of material. So it's nothing in the comparison. Still, they're big. No, they do not have infinite gravity. They are generally not going to be something that advanced societies are afraid of. They'll actually probably be using them as energy sources, as we're going to allude to momentarily. So let's get to the next thing that everyone's always asking about. We've done death from space. We've done black holes. Got to talk about aliens. All right. Yep. Here is our friend Frank Drake with Project Ozma. And again, with this crowd, we might actually know who Ozma was because we have Oz and Ozma. There's a reason that's there. But Project Ozma is named after literally Oz, and we're going to be trying to find the land of Oz, in this case, aliens. Now, the Drake equation is often misused and misconstrued. And so I will simply try and say to you, it is a boundary value problem. It's that classic Hollywood trope, and I need to really lean on trope, because it's not true of, oh, keep them on the phone. We're narrowing in. You see the moment, oh, we get into the United States, and oh, okay, we get to like Illinois, and oh, okay, it's Chicago. And no, it's totally not how it works. That is a boundary value problem. If we get more and more information, we can start saying he's not in this area. He's not out here. He's got to be in here. The answer has to be in this region. And we do this all the time in science in order to say we can't get an answer, but maybe we can figure out what the wrong answers are. We're not going to get so much the right answer, but we can say what is possible and what is not possible. And that's what we get from the Drake equation. Now, as it's listed here, he's saying our number of currently active civilizations in the Milky Way are based on the rate of star formation per year, about 4. You're not making a lot of stars. The Milky Way is middle-aged. It's getting pretty done. It's doing about 4 stars per year out of the 400 billion-ish it has. What fraction of those stars in the Milky Way have planets? Probably all of them. Planets seem to be the debris left over from forming a star, so they'll probably all have something orbiting them. Of those worlds, how many are like Earth? That's interesting because we're starting to learn more and more about that. We've found other Earth-like worlds in the habitable zones of their stars. It's always fascinating to think if Moon hadn't been attached to Earth, and there's fun ways to think about the fact that Moon is not attached to Earth. You can look at its really orbiting sun. Talk to me more about that off this if you want to know more, but it's an interesting story. If that had been somewhere else, Moon would be its own world. Probably wouldn't have been Earth-like. But if we took Venus and pulled it out some, that could have easily been Earth-like. Mars, bring it in some, maybe. Better if we made it a super Earth. Super Earths are the most Super Earths are the most common type of planet that we've been able to suss out in the Milky Way. Twice as common as Earth-like planets. So if we ignore Mercury and Mars, even if we throw in Moon, which we frequently do as kind of terrestrial objects in the solar system, these are subterrans, what we usually call those. You've got Earth and Venus. Statistically, you ought to have 4 super Earths. Now, statistics don't always do exactly what's going to happen. But if we replaced Mars with a super Earth, that's a bigger world with more gravity. More gravity would mean a bigger, thicker atmosphere. A thicker atmosphere means a bigger greenhouse effect. Mars could have been a happier place in this regard. So with tiny changes to the solar system, we easily could have had what is 1, in this case, go up to 3. And point of fact, with a star like Sun, we could easily stack a dozen Earth-like worlds into orbit around Sun. They will not heavily gravitationally interact, and they could all easily host life on their own. So this number could be quite large if the odds just happened to be in the favor of that. All right, and we're working on that as time goes on. But these last 4 are highly problematic. How often does life happen? We have no idea. Just once on this Earth, as best we currently know. Probably everywhere else, but we can't extend ourselves there because we don't know. How often does that life become intelligent? We have no idea. It wasn't that intelligent until 65 million years ago with the end of the dinosaurs, where suddenly having a brain was a winning hand. It wasn't for most of what we call the Phanerozoic era, the era of multicellular life that you can see. Most of that time there was intelligence, but not like what we're talking about here. It was just enough so you can mostly survive and do basic processing. Not what we're seeing basically with the rise of the mammals 65 million years ago. The mammalian brain being huge in comparison to those that came before that. It took Earth a long time to get there, and even longer to get to how often does it become a civilization? A joke, my dogs speak all the languages I do, because they speak none of them, and they know what my tone is. If I say, "Kommen Sie ein?" Like, yes, okay, come on over. Okay, I never taught them German. Groovy. But it's not enough to be intelligent. You've got to be able to build a civilization. Pretty easy on Earth in terms of, when was that? It's 2024, I think we've all got it. Slap a 1 in front. About 12,000 years ago between friends. We can always argue. But again, with Earth being about 4.5 billion years old, civilization is pretty young, as best as we can see it here. And L is even the harder than all of that. How long does civilization end? I'm always off to talk to my students about, please make sure we see Kubrick for so many reasons, but of course, Dr. Strangelove, or How I Learned to Love the Bomb. Because we've certainly come very close to this in the past. I love when I have to say to, even perhaps people in this crowd might not know, when Kubrick was starting up his work, it was meant to be a serious movie. As he learned more and more about the reality of things, it was just funny from how farcical the whole thing was, and that's how he turned it into that. He had to not tell Slim Pickens it was a comedy, or he wouldn't have done it. He thought the role was to be played straight. So the idea here is that there's huge variability. We know this number. We've got a good handle on this. We're working on this. This is garbage. And it means we really can't do much with this. We can get answers that say you're alone or that you've got thousands, tens of thousands, hundreds of thousands of neighbors, which we bring in our Debbie Downer of the group, Enrico Fermi, Italian-American Nobel Prize winning physicist. Because we've all seen Oppenheimer. We all know where we are at this moment. So what's happening is down in Los Alamos, after the bomb has been made, but still when we're hanging out and doing business, physicists are doing what physicists do and talking about what we're talking about today. Aliens and how common they ought to be. And Fermi, being Fermi, very succinctly sums up the whole thing and says, so where are they? Okay, a little bit pessimistic on this. The whole idea, as I always say, careful legal statements. We have absolutely, positively no known current evidence that extraterrestrials of any intelligence have ever visited Earth. As a legal statement, that is like Swiss cheese. There are so many holes that I can pass through there, just like that you're aware of. You would have to know. You could have them crawling all around you. They could be in this room. If you don't know about it, it's not useful to the conversation. I prefer to go with Carl on this one. And his definite statement of the universe is a pretty big place. So if it's just us, it seems like an awful waste of space. So it's just kind of a logic bomb we have to work through. But still, let's try and give ourselves a little bit of an answer, ultimately, as best we can, knowing we can't have an answer. And honestly, this is one of the things I love most about being a physicist, about science and astronomy, is we can approach hopeless causes and have hope in knowing we're going to fail, but we could learn something in the process. So let's do it. We're going to assume the basic idea of what we call the great filter. This is one idea where we say, look, let's argue that Earth and Earth-like worlds are common and that life crops up on these Earth-like worlds. But either before this time, so Earth now, before this time we had all of our starting candidates and they slam into these barriers as we go. And maybe only Earth, a handful, have made it to this point. These are ideas like literally the formation of life, where mitochondria suddenly gets incorporated into life later on. We get to moments here like multicellular life. There's a lot of these, what we tend to call hard steps that happen along the way. We have no idea how many of them there have been. And the idea is maybe we're past the great filter, and that's why humanity is here. Or maybe it's ahead of us somewhere. Thus, I was kind of mentioning the idea of Dr. Strangelove. We have kind of danced with the idea of destroying ourselves. One answer to the Fermi paradox of where are they is to always consider what we call the Copernican principle, or the principle of mediocrity, your average. And currently, humanity is not doing the best job of stewarding the planet. If such trends continue, you might end your own civilization without even a war. And if it ain't broke, don't fix it. If you're average, other civilizations might do the same. That is one possible answer. Could be rocks from space, could be GRBs, could be a lot of things. We don't ultimately know. All we can say is we are here right now. We can also say, if we look back historically, we see a trend line. I'm always often, it'll be again easier in this crowd to say, most things in life that are important are exponential and not linear. We can see on this plot a linear graphing on the x, where we're going linearly through time, but on our y-axis, we have a log plot, meaning each step we do is a power of 10. So each step is very significant on the y and not nearly as significant on the x. And by making this linear log plot, we are allowed to see this progression of basically human speed through time, from the early trains over here, for example, to now, don't miss it up here, we're looking at ideas like breakthrough starshot, where we'll use laser beams to accelerate solar sail nanocraft to anywhere between 10 to 25% of the speed of light. This is likely to be the first way that we're going to see anything up close from a nearby star system. What's very important to notice here is this trend ought to continue. There really is no reason whatsoever to believe that it wouldn't. And from time to time, it jumps significantly, and that's okay. Averages account for jumps. You can have decades where you barely speed up at all, and it can be followed by a big jump, and that's okay. We can plot this as a line through that regardless, meaning we have every expectation that you should keep getting faster and faster. There's no hard law that we can point at here to say this shouldn't happen. Someone might be saying, but what about Mr. Einstein? And I'm going to say, so what about him? Let's have that conversation. First, Mr. Einstein never said you cannot break the speed of light. That's not quite true. The devil is ultimately in the details. Again, talk to me later because I'm definitely smoothing some heavy curves here. But the idea is actually physics has no reason to say that you cannot travel faster than the speed of light. Now, let's get back to that in a minute. Let's assume, though, you're not. We're looking at relativistic spaceflight here, and there are problems. Mainly, as some of us know, the twin paradox. Effectively, the faster you go, the slower your clock moves. If we're moving at really slow speeds, the time we measure of some journey on Earth is the same as we measure on the ship. As we start to speed up, though, ship time slows down. What we're looking at here is just a trip to Vega and back, a fairly nearby star system. Vega is about 25 light years away, which at about the speed of light would take you 50 years round trip. But if you're on the ship, it only takes 8 months. This is a big problem because this is a death sentence for all the people you leave behind. If I get on this ship, go to and from Vega, for me, 8 months passes, all my friends are old and or dead, perhaps, back on Earth. I have not even gone through a year. They have gone through half a century on this. This is why, in general, in science fiction, we see all these star drives that are going to let you have warp drive, for example, or hyperspace, or blah, blah, blah. We've got lots of things in that regard. And again, the important distinction here is relativity and Einstein never, ever said anything about that. As a general rule in physics, unless there is a law that says this is verboten, just no, never. Example, we do not think you can create or destroy energy. We think that is not possible. We always say there is no free lunch in the universe. But we don't have a single law that says you can't travel faster than the speed of light. We have a concern. And the concern is different than the law. The concern is anything that travels faster than the speed of light is a time machine. And then you're dealing with problems of causality. We start having grandfather paradoxes and all kinds of things happening where cause and effect can easily swap themselves. But again, there's no rule against it. We just don't like it. Well, nature doesn't care what you like and what you don't like at all. This is where Hawking will have his, no causality conjecture. The basic idea is that if you ever try to build something that travels faster than the speed of light, something will happen to prevent it from actually working. And again, we have no evidence towards this, but it's important for me to say, one, it's possible. Two, it's not necessary. We can do this without traveling faster than the speed of light. We see here an idea of what we had, the work of Freeman Dyson, a Dyson sphere, where we're building a large-scale structure, in this case by disassembling Mercury. And this would not be the right way of doing it in this artistic perspective, but I like it more than what I was going to show you without it. This is a Dyson sphere. We're going to make it solid. If anyone wants to think about Tabby Star and what's almost assuredly not happening there, this. Groovy. What would be more likely is a Dyson swarm. Why? It's easier to control, and we are going to use very simple technology. Bear with me. We're going to take metal and we're going to make it shiny. We call it a mirror. We're going to make lots and lots and lots of those mirrors and put them in orbit around the sun, and they can just focus their energy onto a source. You've already done this on Earth. This is an easy, easy thing to do. For my money, again, with the crowd here, I think I can say, practical fusion, just 5 more years away, since 1950. All right. Any old time now would be lovely. I view this as your first practical fusion reactor in reality. While it seems kind of pie in the sky, as we have larger and larger heavy lift rockets coming online, it's not going to be hard. We're advancing the ideas of 3D printing to just send robots that are going to do most of the work to Mercury, and it's slow at first, but it picks up in time. And we need this because we're going to try and colonize. If we can't find them out there, then we'll start going and doing it for us. Oh, location, location, location. This is what we call the coral model of colonization, where you play a little dumb in this regard. You don't quite know where you're going, and that's kind of how coral ultimately evolves. We send out a branch, and those branches send out branches, and those branches send out other branches, and we expand like this. And what I want to try to impress upon you is it wouldn't take long to colonize the entire galaxy doing this. I'd be quick to say this is not the most efficient method in any way whatsoever. But even if humans were very blind, meaning you pick a bunch of stars, you go, oh, we're going to go here, but there are no planets around that. You're being a little silly. You didn't look before you left. Even if you're doing that, even with really, really, really slow star drives, we can go back here for a moment. If we're traveling at like maybe 0.1 C, all right, that problem is not there anymore. We're not worrying about leaving everyone behind. You could easily colonize the entire galaxy in about the time between you and T-Rex, about 65 million years, which is, astronomically speaking, nothing. Absolutely nothing. So, of course, this poses a big problem, because I've tried to say to you that colonizing space is actually kind of easy if you were going to put your mind to it. Yes, it would require way more energy than humanity currently is building, or excuse me, producing, but still, that's why we're looking at your sun. We don't need to build anything new. The idea that I've given you only uses current technology. I can start doing this today if we wanted to budget for the whole thing. We could do it better in a few decades, but this is not like centuries or millennia away. I am always going back to certain annual reads for myself. And right now I am doing the classic Jules Verne, 20,000 Leagues Under the Sea. And all he was doing as he's putting this together, if you've never read the book, he's, as he generally does, he's a bright guy. He's citing all the scientific papers and discoveries that he's using to put this story together. He wasn't just magically saying this could be. He's like, no, this is going to happen, and this is kind of how it's going to happen. He wasn't so much looking forward and being a futurist. He was just prescient about the technology that was available at the time. And if you wanted to apply yourself to that, that is where you could go. It's the same kind of discussion I'm having with you here. I definitely want to say I'm not calling myself Verne in this regard. But still, we want to try and have an answer. Why haven't we seen anybody? Well, without more time, I can't dig too much into the idea that it really looks like humanity's early, meaning that you showed up to the party earlier than we think others would. And there's good evidence for that. Again, talk to me maybe in the questions, and we can hit that a bit. But if you are indeed early, which seems to be the case, then it means you have an opportunity to have a land grab. And that's what you're seeing in front of you here. Basically, the top peak that we see with each of these kind of outward points is where you start. And so they're randomly distributed throughout space. Don't even think star systems or galaxies, just think random spots in space. And the idea is eventually you just start to spread out. Once you start getting faster and faster, you start to spread out. And you're going to, as I showed you a moment ago, keep getting faster exponentially with time. As you do so, avoiding the whole time machine problem, we'll go with maybe you shouldn't travel faster than the speed of light. What this shows us is what we have here. And the red lines, this is a space-time diagram where we're just going to have space on our x-axis, time on our y-axis. The red lines delineate the speed of light, always at 45-degree angles on such a plot. And what we see is anything within our red lines is something that you could have seen historically. Back here is the past. Above this point, because we got us here now, is the future. Okay? So this is the beauty. When you look at your hand at arm's length, it's a billionth of a second ago. It takes about a billionth of a second for a light to go from hand to eyeball. The awesome nature, I think we all know in this room, of astronomy. You're looking back in time. It's like the only legit time machine. I love that about what we do. I study things on the far, far, far end of creation. I'm always trying to push it farther. I find that exceptionally neat. What we see here, though, is we include this inner kind of yellowish region. Now, the width of this region is dictated by the speed at which we're expanding. Again, kind of going back to here, we're saying we're going to slam into each other eventually. We have all these random starting points. We're eventually going to say, we're all going to be nice neighbors. We're all just going to, when we meet, we go, cool, that's the line. As if that would happen. But We can talk about that. The faster they're moving, the thinner the regions are that you could see. And this is one answer to why you aren't seeing them. This great cosmic land rush has begun. I always have a joke, Missouri's the sooner state because of some very interesting historical moments where basically you were supposed to grab some land, they were supposed to say, go, and everyone runs out and grabs some land, and a bunch of people just decide, I'm gonna do it sooner. And they left, and they tried to grab a bunch of land before all the people who wanted to follow the rules could get there. And that's kind of the idea here between, this is the Gravity aliens solution to the Fermi paradox. There, of course, there must be an answer. We don't know what it is. This is one of them. If aliens effectively doing what you're doing, growing with technology exponentially, getting faster over time exponentially, starting to move into space exponentially, you're eventually going to start spreading. And you'll start getting faster and faster. If I am moving very, very rapidly at you, imagine I'm going 90% of the speed of light. What this means is you will get the information that I'm coming at you moments before I arrive at you. Because light is the messenger. If I'm moving really, really slowly, light has all this time to get to you. But the faster I'm going, the photons don't have a lot of time to get ahead of me. As the information that I'm coming, you go, oh, aliens. I'm like, hi. Because I'm right behind those photons. And so this could explain it. They're all out there and they're starting to already move, but that colonization rate is so high that it precludes us from yet seeing them. As always, this is just one fun way of trying to explain what we see around us. Namely, it seems like humanity's early. I will give a little bit on that. The universe is only 14 billion years old. Could have had life at least starting 11 billion years ago. Most stars live for way, way, way longer than that. So why are you here now? Life could have started at any time, and there's far more time in the future where we're not at what we might discuss as like the heat death of the universe compared to this barely happened moment between the Big Bang and now. There's just all this time up here versus this time back here. Why are you here when you ought to be somewhere in the middle of this pack? That's a tricky piece of business to explain. And the solution here is because if you weren't, you wouldn't be here. As soon as this expansion happens, the game is over. That's where we'll probably end today by me saying, if that didn't make sense, when you develop some kind of a new place for humans, whether it's a shopping center or a home, you don't stop and look at the squirrels and say, hey guys, are you gonna like become a civilization in a few like tens of millions of years? Yeah, okay, sorry about that. No, you just plow right over them. If you weren't there at the start, you're the squirrels and you got plowed over. Under the best circumstances, your cosmic overlords might be like, all right, we'll let you stay there. That planet's yours. The rest of them are ours. Have fun. And that kind of business. This is all about who gets there first. There is a very large incentive here for what in game theory we call a first player move, where there are several games out there. That's why winner usually has to play second in these types of games, so you don't keep having that first mover advantage. There are a lot of good reasons that you would want to move out into space as quickly as possible. And again, with most of my talks, this is where we Ouroboros, such as all those problems, death from space we talked about at the beginning. Thank you very much, everybody. I think I kept it on time.
I think my brain's full. My feelings.
Questions, comments, answered. What can I help you gang with? The meaning of life next, 42. Excellent.
Is anybody considering that entanglement might be a potential way to get from A to B?
You can link that over to, so I get that one a lot. The quick answer is no, but if you want to play with it, the idea is maybe. And the closest idea in science fiction to that is actually if you go back to either the new or old Battlestar Galactica, where they're going to use what they call a jump drive. Yes. And the idea effectively is, in Star Trek, it's kind of like the long distance teleporter, if you like that, where I can wiggle something over here in the universe and have something really far away wiggle somewhere else. Again, we are dealing with a time machine because I can wiggle it's a telegraph. I can tell you about something that happens before you see it. And we do have some issues with that. Remember, no rules that say you can't. But in theory, yes, you could probably do this. The energies involved would be obscene and technology way, way beyond us. With the description of what I'm saying in terms of spreading out into the galaxy and beyond, we'd be using really low tech. In fact, the whole idea of building the Dyson swarm around the sun, you could use lasers, and we already have that. That's already the current idea for breakthrough starshot. So everything there is using current tech. We don't need anything pie in the sky. You can also achieve this with very long rail guns. We've already built stuff like that. There's a lot of ways to achieve very, very high speeds without invoking any exotic material, exotic technologies. We try and look at this within what we call future tech without going into where we think things like Planck's constant, the speed of light. We try to put these as hard lines and say we don't expect we're going to get beyond these. If we do, wonderful. That might open some doors, but we don't want to make those assumptions. And so we try to keep it as kind of MacGyverish and duct tape and WD-40 as possible versus trying to say, oh, let's build some really crazy new starship. Keep it simple. What else? Clear as mud, as my advisor
back in the corner.
Explain the Dyson sphere concept. That's a new one for me, but just to build on again.
Sure. So Freeman Dyson, it's funny. I was at a joke. URI has their slogan, their motto: "Think big, we do." And Freeman Dyson would just laugh at that. Dysonian engineering guy is named because it's just taking anything you could think of and then blowing it up to the biggest possible scale. And so Dyson said, and you can kind of see it in this image a little bit, there's oceans and land back here. You have Earth, which is a lovely spot, but in about 1 billion years, the average temperature on Earth between friends, everywhere, always, will be about 120 Fahrenheit. And another 1 billion years, the oceans are going to boil off. Earth is not a forever thing. You could save this by like literally pushing Earth farther and farther out as time goes on. A classic piece of science fiction, Gorath. I think that's 1962. Go see that, where that's the premise of the film. There's an asteroid coming at Earth versus, rather than moving the asteroid, they move the planet. Okay, but you can totally do it. So I love it. It's just wonderfully terrible Japanese cinema. I love it so very much. If you get the right version, you can even have the walrus kaiju, which is amazing. But back to this, the idea is that we could easily house trillions, tens of trillions of human beings on a structure like this. You effectively have a near unlimited, at least at this point in time, energy source to keep your civilization going. Some people might want to talk. I heard some snickers when I talked about Tabby Star. The idea here is that your star, if you did a complete sphere, would disappear. You would be able to see heat coming out of this thing, and that would be something we've looked for. Can we see heat signatures in space where we don't see visible signatures of a star? That might be the idea of seeing a Dyson sphere. But the idea is, as I said, rather than functional fusion reactors, which literally might never work, we don't know. They should, but I'm serious with the classic trope. Every 5 years, oh, we're almost there, we're almost there. It's been working for 4.5 billion years. If it ain't broke, don't fix it. And this is using solar panels effectively. Now, this is showing some exotic technology. We don't need to do anything like that. Keeping a sphere around your star would really require advanced technology. We would not be able to do that yet. But a swarm is just a bunch of satellites. We've got that. We're doing that around Earth right now. And so the idea would be basically build a large solar farm on Mercury. We can do that. We're doing that in Rhode Island, for crying out loud. We build a big 3D printing plant next to it where we're printing miners, assemblers, and our reflectors. And we can launch them into orbit of sun, again, using like rail guns. I joke with my students, get a bunch of hamsters on wheels to pull back the slingshot like Wile E. Coyote. That would work just fine. That would work just fine. We have no atmosphere on Mercury. We have low gravity. We don't need rockets to get this done. And you put little Hall effect thrusters on them for fine tuning. We have the computational power to keep a massive swarm like that going. And just using mirrors, you focus that light down to collection areas. Again, technology we already have. This is oldish technology here on Earth. And you are collecting huge amounts of that energy. Even if we assume terrible efficiency, it's just, this would power you for a long time before humanity might be like, we're going to need more than this. And we allow for that. Again, the same idea of exponentials. Humanity's energy growth is just up, 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 up. We're not seeing any plateau to that anytime soon, but this would really solve it all for a long time. It's kind of the ultimate green technology, honestly. Nothing is really as renewable as this is. Does that help? Excellent, certainly. Yes, sir.
Where would those energy collectors be, and how would that energy get to Earth or wherever we're wanting it to be sent off to?
Great question. The question is, where will the collectors be? How are we going to move that energy around? Lots of options. It would depend on how we ultimately decide to construct it. You could, for a while, we only need about half of Mercury. I know it sounds weird to do the whole game. I say that tongue in cheek to say you don't really need to get rid of much. There is a thought process to solar system ecology. Kind of everywhere humans have gone historically, they trash it. And so this is an idea of Martin Albus at the CFA, the Harvard Smithsonian Center for Astrophysics up in Boston, saying before we start going anywhere else, maybe we should think about this. I joke when people say, have we gone to moon? I say, absolutely, we left trash behind that you can see. So it's easier, as I say, the true story is better than the false story always. Back to this, you have a lot of options. It would probably be best to, at this point in time, for cheap and easy, just make large molten salt piles that we can use. You can store it as heat, and then we can kind of send it as microwave lasers or anything else kind of here, there, or everywhere. They aren't efficient. That's the same conversation that's happening. Do we want to build giant solar farms in space around Earth and beam the microwaves through the atmosphere? And it would totally work, and don't be worried about the microwaves, that's fine, but it's really inefficient. It's so inefficient that that doesn't work well, but it's the atmosphere. If I get rid of the atmosphere, the problem almost entirely goes away. So I can move that energy easily, for example, from around the sun to moon. And then that energy could again be transformed into some other form of energy. You could think about us mining, refining uranium, plutonium, for example. It's one of our best energy sources right now that we can actually make work. Is fission reactors. We could be kind of using that energy to do that. There's a lot of different mechanisms towards that. Cool. What else? Clear as mud.
Would you be around a little bit, so if
Yep,
anybody
yep.
else wants to, okay. Well, thank you very much.